Hello, in this video we're going to be talking about endergonic reactions. So let's not waste any of your time, let's get right to it. Now, just like the previous video, when it comes to notes, this one doesn't have any text at the bottom like the previous one did, but you certainly want to capture all the information inside the graphics and the figures, the diagrams, loaded with multiple choice question potential. So be sure you capture all of that. When we're talking endergonic reactions, okay, again, it's associated with building molecules. So if it's associated with building molecules, we know we're going to be storing energy inside of the product, whatever the molecule may be. That energy will be potential energy. We know that if we're building a molecule, we know that the anabolic pathways will be used. We know that dehydration synthesis will be involved. We know that it's endergonic reactions. That's what we're talking about. But it's the idea of endergonic reactions. So we're ending up with a product. Again, if you were in a chemistry class and you were putting solutions together in a beaker with the purpose of making an endergonic reaction, what it would look like in the end is that there'd be some sort of product formed. Maybe it's a yellow blob of something or purple something, but you'd get a product, much like when you take sodium and chlorine and mix them, you get a product, you get salt. Okay, so that's the idea of an endergonic reaction. Again, if you look at the graph, you can see the far left, the energy level is not surprisingly, hopefully, at the same level that the exergonic reaction ended. Okay, because there's almost no energy in the situation. But as you build that molecule, okay, you can see now that the end product is above. It's up on that y-axis, the energy amount, which tells you that when you get your product finished, okay, energy is stored inside of it, that potential energy. And that's why endergonic reactions have a positive G, or a positive energy, because energy is stored inside of it. You now have more energy than what you started with. So it's a positive. You've added energy. And because you are building a molecule, okay, it does require an input of energy. You're making something. Of course, an example would be photosynthesis. But because it requires that energy, and you're putting something together, that will not happen spontaneously. I mentioned the reference to the room, cleaning of the room. The cleaning up takes time and energy, whereas the messing up of the room could have taken maybe a week to get it fully messy, and just a little bit at a time. A pair of clothes there, a book here, a plate there, but to clean it all up at one time takes energy. By making a molecule, since you are storing energy, that potential energy, it's not moving, so therefore you are decreasing the entropy, you're decreasing the chaos of the situation. And those are angles and ideas that we'll talk about when we get to the laws of thermodynamics, which might be two away. But it's the idea of building the molecule, so in your final product you now have something that is storing energy. Okay, but again, with the purpose, for the most part, of being broken apart, so you can get that exponential release of energy. Excuse me. Much like when we talked about with the firecracker, it takes a little bit to put it together, but you release a lot of energy when it explodes. And I guess that's something to think about. If a firecracker that's already made is in the right situation, okay, it can explode spontaneously without you even doing anything. Maybe it's on the ground near a campfire, and a spark from the fire jumps out and lands on it. Okay, then it's going to have a chemical reaction. It can happen spontaneously, but all the components to make a firecracker could sit on the table next to each other forever, and the firecracker would never be built unless somebody took the time and the work and the energy to make the firecracker. Once it's built, it can break apart spontaneously or naturally, but they could never be built. Just like if you take a chair, a chair sitting outside in the weather, in the sun, in the rain, and whatever, over time, slowly, could break apart naturally, just from wear and tear and the effects of heat and water. But you could have all the components of that chair sitting beside each other on your deck or on your patio, and it would never come together naturally or spontaneously. And so that's the big idea, the big difference in that concept. So that is our video over endergonic reactions. When we come together next time, we'll be talking about redox reactions. So we'll see you then.